Okay, any questions about the exam? Is everyone clear on what entropy is? Okay, looks like everyone is clear on what entropy is. That's great. So good. So we will continue. This is the final Zoom session. We will not be meeting on Zoom anymore after this. My life will have a big vacuum, but that's okay. We will live. And I know we haven't been able to revise all the topics, but I've tried to go through the early ones. So which it's been a while since you looked at them. Apart from that, you still have 2 days. The exam will be released Friday morning. I would like to see a response rate of 90% in the course evaluations before I release the exams, because otherwise the evaluations become subject to whether you're liking the exam or not, and it's bad either way. If you find it too easy or too hard, I don't know. It's best to do it before that. So please try to do it. Only 53% have responded so far. Please try to get it up if you haven't, if you have, thank you very much. If you have, please try to do it. I sent the link on Slack and also through email. Great. So we will talk about Carnot cycle today, which is, we'll start with Carnot cycle, which is a particular, so thermodynamics is full of cycles, meaning you start at a point A and you do something to go somewhere else and you come back to point A. So of course, there can be infinitely many cycles. Some of these cycles can be reversible. Some of these cycles can be irreversible. What we are trying to prove here that entropy of point A, entropy at point A is uniquely defined by what point A is. It doesn't matter how you did, what you did, whether you went out along 1 and 2 and 3 and 4 and you came back to point A, or you did something else in order to come back to point A, the entropy will always be the same. That was the idea in proving this Carnot cycle thing. So Carnot cycle comprised 4 different parts: isotherm, adiabats, isotherm, and adiabat. Again, this is a useful exercise to become familiar with how to calculate entropy change. And if you notice over here, there was a 3-step process. We started with an ideal gas. For an ideal gas, we showed that this specific cycle, Carnot cycle, will have net entropy change of 0. It will not depend on what you did. If you come back to A, it's going to be 0. In order to prove that, we started with the different steps, 1, 2, 3, 4, calculated the entropy changes separately and added it up. So why did we add it up for different steps? Because we are doing it only for this cycle at the moment. So, and here again, we had these subtle arguments. You can see du is always dq plus du is always dq plus dw. And whenever you make arguments such as this, if you have an isothermal process, you know that du is equal to going to be 0. For an ideal gas, it's not going to be true in general, but for an ideal gas, it is going to be 0. We saw this last time also, because du is cv dt plus pi t dv. For an ideal gas, pi t is 0. And if you're talking about isothermal process, d2 is 0, therefore. So from this, and we did similar manipulations for all 4 steps, and we were able to show that delta S is 0 for Carnot cycle for a perfect gas. Next step got interesting. We looked at Carnot cycle for any gas. We are still looking at Carnot cycle, but for any gas. How do we do that? In order to do that, we did a proof by contradiction. We constructed 2 engines with different efficiencies. So in order to do this, we introduced the notion of efficiency, which is 1 minus QC by QH. We had 2 engines. We ran one of them forward, one of them backward. And the idea was that this engine over here has higher efficiency than the engine on the left. So it means you need to do less work to run this engine than you can generate out of that, than the work you can generate out of the first engine. So this is Pakhra running around crazy. So that was the idea here, that WA is more than WB because this engine is more efficient. So you can run this one in a forward direction and this one over here in a backward direction. And then you can look at them together and it will appear as if you have only one engine where you are violating one of the statements of second law of thermodynamics. It seems as if you are taking heat from a hot source and converting it into work 100% without any loss to a cold sink. And that was how we proved that Carnot cycle works. Carnot cycle has delta S is equal to 0 for any gas. For the third part, where we showed that delta S is equal to 0 for any gas, not just Carnot cycle, but any cycle, we took a generic cycle, and you can imagine like a quilt. You have some blanket or a quilt, and the quilt is made up of little patches. So we imagine that the quilt is made up of small Carnot patches. And then we showed that since we already showed that it's going to be 0 along any of these patch, we showed how it summed up to be 0 for the whole thing. So this was our proof of Carnot cycle. If you're running short of time for your exam, the most important thing out of this proof would be to do the step 1 right. I think step 1 is very good practice. Step 2 and step 3 are slightly abstract. They're easy, but slightly abstract. Step 1 is good practice. It allows you to work through many of the basic things underlying this semester. Okay. So we proved this, that delta S is equal to 0 for any cycle. And the thing that is more important out of this that came out later after this class was the Clausius inequality. So Clausius inequality is all super important because then it led to our notions of free energy, which of course dominated the remaining part of the semester. So here for Clausius inequality, what did we do here? The idea was that for an isolated system, we saw that second law of thermodynamics says ds more than equal to 0. But if it is not an isolated system and some heat is being given to the system, we proved through this couple of pages, and it's worth going through this proof, that ds more than equal to delta q by t. So if you're giving a certain heat to the system will go from some point A to some point B. You know what change, you don't know what change the system will do. But one thing you can say for sure, two things you can say for sure. One is that, by the way, if any of you are interested in saying hello to Pakara, there he is. My wife has just left for her lab to inspect something, so he's quite upset that she has left. So he's looking out on the window. Hey, Pakara, say hello. Oh, he's not interested. It's too cool. Okay, so, and some of you will meet him for ice cream next year. So if it's an isolated system, then we can say that ds is more than equal to 0. The entropy always increases for an isolated system. But if it is not an isolated system, the entropy, we can say two things. First of all, if it goes from point A to point B, we know the entropy is uniquely defined by point A and point B. So it makes sense to talk about ds, the total derivative, the exact differential, right? We don't have to do a delta like over here. We don't have to talk about inexact. So that's the first thing we know. We can talk about ds, just the difference between the two states. And secondly, we know that the ds will be more than equal to the heat given to the system divided by temperature. This is what we proved over here for Clausius inequality. And this inequality becomes equal when the heat is being given reversibly. When the process is reversible, the entropy change is equal to delta Q reversible by T. And that's kind of the nice thing about calculating entropy change. If you have a system going from A to B and you have some complicated path that you're taking to go from A to B, it doesn't matter whether this path is reversible or irreversible. You could imagine some other path that you execute reversibly and calculate the entropy change along this reversible path. Calculate the entropy change along this reversible path by using the formula delta Q reversible by T, and you're fine. So you can use this to your advantage to calculate entropy change. Okay, we will continue our whirlwind review. Let's go to next class. Yeah, so we recapped this, and I talked a little bit about the molecular definition of Entropy, again, I'm not going to cover this because we are not going to talk about this in the exam at all. S is equal to K log W will not be there. We'll go back to the traditional review where we use the fact now that ds is equal to delta Q reversible by temperature. So we can write down an integrated form of this equation that S of a system A, of a reactant A, of a chemical A at temperature TF can be calculated from 0 Kelvin to some final temperature TF by just doing this integral, delta Q reversible by T. Here, we did not know what is the value of entropy at 0 Kelvin, so we introduced third law of thermodynamics, which makes sense from the S is equal to K log n ln omega formula, because quantum mechanics tells us that omega is equal to 1 at 0 Kelvin. That's something you will do in 482. So it means S is equal to 0 at log of 1 is equal to 0, so S is equal to 0 at 0 Kelvin. But for now, we just take it as a theorem, as a law, as a postulate, which is given to us that entropy of any substance at 0 Kelvin is 0. So we can write down SA at a temperature as 0 to T, delta Q reversible by T. And later, we will talk about phase transitions, because this has to be, there is nothing wrong in this formula, but if you're undergoing a phase transition, you have to separate it into some special parts in order to calculate it. Okay. Cool. So where were we here? We came to this formula and then we said, okay, let's say the reversible path is actually happening at constant pressure. If the reversible, he's looking very closely. You want to join class, Pagoda? Hey, look who it is. It's your friends. So if it's a constant pressure reversible path, then delta Q reversible is the same as CPDT, right? We talked about this last time also, that change heat given to a system at constant pressure is equal to change in enthalpy, which is equal to CPDT. So we can use this formula, and CP we can measure in experiments. We have ways of doing it. So we can calculate our entropy going from temperature I to temperature F. However, this does not account for entropy change during phase change. So the thing to keep in mind here is that this equation is exact. When you say STF is equal to STI plus TITF delta Q reversible, this one, however, has an approximation. It is saying that there is no phase transition, because at a phase transition, you don't have to just consider for the heat capacity of the substance. You have to consider for the energy that is given for the phase transition itself. So because you're changing phases, so the heat capacity itself is changing discontinuously. So the other reason why this is inexact, it can be made exact, is because the CP itself changes for the phase A, for the initial phase to the final phase. So to account for phase transitions, we said that if the phase transition is happening at a constant pressure, and this was our glimpse into phase diagrams to come later, then Q is equal to delta transition H, the change in enthalpy at that temperature. And we have a particular temperature at which the phase transition happened, T transition. So we can write down the entropy as 0 to some temperature TF, T fusion, let's say, at which the fusion happens or melting happens, CP for the solid phase. Now you have solid to liquid going on. You calculate delta latent heat of fusion for the melting reaction divided by the fusion temperature. And then you put in the heat capacity for the liquid and go from fusion temperature to the boiling temperature. Once again, you reach the boiling temperature, you calculate delta the vaporization enthalpy divided by the temperature of, this is S of system only, yes. This is S of system. So that's a very good point, Elizabeth, because Clausius inequality is wonderful because it allows us to talk about the S of system. That's why it was nice. Yeah, this is all S of system. So this is what we did. This is quite useful when you are looking at a chemical reaction. And of course, you could have more phase transitions happening, and you could generalize this without any problem. Now we came to something which is super important, and I'm ready to bet that many of you will forget this slide, this page, a few months from now. And I hope you don't. This is where thermodynamics, if you go and speak to people who took PChem many, many years ago, 10 years ago or so, most of them remember energy. If you ask them enthalpy, they get confused. They're like, oh, strikes a bell. I don't remember. Free energies, they definitely get confused. And if you ask them to talk about what is the direction for spontaneous change, that's where people forget. So try to pay attention to this slide. There will be questions on this slide in the exam, because there's no way we don't have questions on this, because phase diagrams completely follow from this one. So much of what we did beyond this class, 19th of October, was just using the material on this slide and the next couple of pages. So this is, I'm talking about 1019 when we talked about spontaneity. So we said that second law of thermodynamics says that the direction of spontaneous change is delta S total more than zero, right? The entropy increases. However, for a system, we can write down Clausius inequality. We can say ds system is more than equal to delta Q, heat given to the system, right? So this is still a bit clumsy. The reason it is clumsy is because you have a total derivative on the left side, and you have an inexact derivative on the right side. What if you could express this spontaneity condition for the system, not for the universe? We already know that the universe changes, the arrow of time moves in the direction of the entropy of this whole universe increasing. But for the system, how do we do this? So here, in order to do this, we took two views. We looked at constant volume and we looked at constant pressure. At constant volume, and we looked at only pressure volume work. So at constant volume, first law of thermodynamics says du is equal to delta Q minus P dV. dV is equal to 0. Therefore, du is equal to delta Q. So this inexact differential can be replaced by a total derivative du. Similarly, at constant pressure, delta Q is equal to dH, and this inexact can be replaced by dH. So we get two statements now equivalent to Clausius inequality, one of them valid for constant volume, and the other one valid for constant pressure. He's really, I think he has a sense we are all going to leave. Hey, what's happening? You want to tell them about, you have any last moment tips for thermodynamics? Bahora, would you like a treat? Treat? Would you like a treat? I'm not giving you a treat right now. I'll give you after class. I might have to give him a treat now because I have triggered his treat sense. Okay, great. So we have ds more than equal to dH by T for a constant pressure process. It still involves two state functions. So this is where we introduce two new state functions. So this can be rewritten in the form involving only one state function. We defined the Helmholtz free energy and we defined the Gibbs free energy. Helmholtz free energy was U minus Ts. Some books will call it F instead of A. The notation changes, but it is always Helmholtz free energy. Other book, and then we have Gibbs free energy, which is H minus Ts. And it is easy to show that under constant volume, TdS more than equal to du is the same as writing dA less than equal to 0. And TdS more than equal to dH is the same as writing dG less than equal to 0. This is where people get confused sometimes, because there are two forms of spontaneity. One is to say that ds universe more than 0, and the other is to say dA system at constant temperature and volume less than equal to 0. Okay, he's protesting. I have to give him a treat. Give me a moment. Huh. I'll be busy. So notice these sign changes. For entropy, it was more than 0. For free energy, and you would invoke Helmholtz free energy or Gibbs free energy, depending on whether it's a constant volume temperature or a constant pressure temperature process. One of the things we did after this was to look at the physical interpretation of change in A and of change in G. I'm not going to go through the proof. I want to emphasize the final result. The result was that change in A is the maximum work obtainable from a system at constant T. So this was interesting. Even though we defined spontaneity condition had dA at constant temperature and volume, right? And dG at constant temperature and pressure. But when you think about the interpretation, the physical interpretation, this constant volume disappears for A. It, however, does stay around for G, and that's how the math is. So change in Helmholtz free energy is the maximum work you can get out of a system when you are running it at a constant temperature. While change in Gibbs free energy is the maximum non-expansion work. Remember, because so far we had been only talking about dW is equal to minus PdV, but there is other work also that can happen, right? dW non-expansion. So dG tells you about the maximum non-expansion work you can obtain from a system. But however, now you have both constant T and P. By the way, I will send out the final list for participation points later today or tomorrow by latest. I think almost everyone is good in that, but if you don't see a name there, talk to me separately and we can still figure out something. Okay, so, and we looked at an example, 3D1 in Atkins, where 1 mole of glucose is oxidized, and we talked about using these interpretation. Is final going to work in a similar way to the first midterm? Yeah, exactly. It will be released morning of Friday. That's when Slack stops the moment final is released. No, if you ask me any question on Slack, you can ask me questions about the exam on Slack. You're welcome to. Most likely you will get an answer that it is correct. There is nothing wrong. It is sufficient as stated. If it is not sufficient and you indeed found something which is a bug or a problem, I will report it to everyone through email and through Slack. But otherwise, the exam should be clear in what it wants you to do. It's a similar exam. You have more time to do it. It is due exactly 1 week from now, so it is due from the release date. So it's due on 18th in the morning, and you will have your grades in a couple of days after that. Okay, so this is when we introduced A and G. That's why this was an important class, because we introduced these two. Will homework 7 grades and solution be released before Friday? Is Connor there? Connor's the boss. Connor, are you going to release 7 grades and solutions?
I'll finish by today, I think.
Okay, thanks, Connor. Yeah, they will be released. And okay, so let's go to next one. So the direction of spontaneous change can now be written as in 3 different ways. It can be written as ds, 4 different ways actually. It can be written as ds universe more than 0. It can be written as ds system more than delta q divided by t, or it can be written as dA system at constant. So in general, A and G, we stopped writing system and universe because that was the whole idea. That's the reason we introduced them, because once you have A and G, they kind of account under constant temperature volume or constant temperature pressure. They account for everything. So system is, we don't need to specify system. It's already there. So this is our conditions for spontaneity, and they are all equivalent. There is no difference. They carry exactly the same amount of information. And then this class, we proved that the change in G is indeed the additional work at constant temperature and pressure. Now comes a super important relation. Again, this one is also quite important. So we are talking about 1021. On 1021, we introduced for the first time the integrated first and second law of thermodynamics. And the reason why this is very important is because you might forget all of thermodynamics, but if you remember this relation, you can derive so many things that follow from here. So to do this, we just wrote down our first law and second law and joined it together, and we got du is equal to TdS minus PdV. So this contains all information about first law, it contains all information about second law, and when you do that, you can see the natural variables for U, and this is where we introduce natural variables, are entropy and volume. For a constant composition system, if you have a variable composition system, you have to add n, S, V, and n, right? So for U, the natural variables are entropy and volume. This is something which is easy to forget. If you forget this, go back and think about integrated first and second law of thermodynamics. In a take-home, open book, open internet exam, just so this one will also be open internet. You can't talk to your friends or your family or things like that. You can talk to your dog. That's allowed. Yeah, so this relation is super important. du is equal to TdS minus PdV. And we just saw that U is the natural variables for U are entropy and volume, and number if you have a constant, if you have a variable composition system. So since U is a function of S and V, we can write down using our multivariable skills as du is equal to partial U by partial S at constant V plus du plus partial U by partial V at constant S multiplied by dV. We could have done this for U as a function of, I don't know, pressure and volume also. We could have done it as U as a function of pressure and entropy also. Such an expansion could be done for any of these, right? The fact that you could write down such an expansion doesn't depend on whether they are natural variables. We are doing it in the natural variable form. Once we do this, we compare this equation over here, du is equal to this thing, with our integrated first and second law. And we compare them term by term. We say ds and ds, let's compare the term. So we get t is equal to partial u by partial s at constant v. And then we compare minus p with this term over here. And we get minus p is equal to partial u by partial v at constant entropy. This one over here is the most fundamental definition of temperature, because it really comes from natural variables. So it means it has all information about first and second law. This brought us to another beast of PChem 481, which is Maxwell relations. But if you have paid attention till this point, I really hope that you can see that Maxwell relations, while hard to remember, are really quite simple. Why are they simple? This idea is that if you have a function written as df is equal to gdx plus h dy, and if this thing is a total derivative, what does this mean? It means you're talking about ds or dh. If you were talking about delta q, then that won't apply, right? Because that's not a total derivative. That's an inexact differential. But for total derivatives, for this to be true, we must have the second condition that partial g by partial y at constant x must be the same as partial h by partial x at constant y. So partial g by, or in other words, what it is telling you is that if you take a function as function of two variables, these two things are going to be equal. It doesn't matter which order in which you differentiate this function of two variables. You can differentiate with respect to the first variable, keeping second constant, and then the second one, or the second variable keeping first constant, and then the first one. The answer should be the same for any total derivative. And this is all there is to Maxwell relation. We look at du is equal to TdS minus PdV. So g becomes t, h becomes minus p, and we get a relation, partial t by partial v at constant is equal to this. So Maxwell relations are easy to derive if you start from the integrated first and second law of thermodynamics. We just did one for u. We could do it for other state functions also. We could do it for g, we could do it for a, and we could do it for h. For all four, we can do this, our favorite state functions, and we get separate Maxwell relations. They are hard to remember. The exact relation itself is hard to remember. Hey, shut up. I don't see directly as to why this might be true. It's hard to derive it, right? You have to go through the math and get over there. It's his girlfriend, the other side of the road. Her name is Shelby. He's 7 times older than him. So that's our Maxwell relations. They look so mathematical and kind of boring, right? That you have partial p by partial t at constant v is equal to partial s by partial v at constant t. What are you going to do with it? They turn out to be extremely useful. You yourself have used it in a variety of points in your homeworks. In fact, it was quite common before we did Maxwell relations on the homework exams. On the homework problems, you would ask me, can we use the Maxwell relation in this? And you can go back and look at some of your homework 1 and homework 2 problems, and you will see that they actually become easier if you directly use one of the 4 Maxwell relations. There are books that give you tricks of how to remember the Maxwell relation by drawing things like H, A, F, G, and then P and V, and things in the middle. And in a COVID has changed so many things, and in an era where everything is open internet, I don't see the point in remember these things. If you know where to find the Maxwell relations on the internet, and if you know how to derive it, committing it to memory seems kind of pointless to me. And I can't ask you to do it because I was never able to remember it. It's just I had to derive it or look it up on the internet. So why should you remember it? If you do, bravo, wonderful. But I don't expect you to. However, I expect you to be able to explain to a professor in 10 seconds as to what is the idea. How would you go about deriving Maxwell relations? And that really boils down to saying du is equal to TdS minus PdV is my integrated first law and second law of thermodynamics. This means that partial T by partial V at constant S is equal to minus partial P by partial S at constant V. Here you go. This is my first Maxwell relation. This you can always easily derive. The other ones you have to now go and use. A is equal to U minus TS, H is equal to U plus PV, and write down similar integrated first and second law of thermodynamics in terms of these things. And from them, you get your Maxwell relations. So they are kind of hard to derive, but we did applications for this for van der Waals gas. And we got a very interesting relation using Maxwell's relation for van der Waals gas. We showed that the internal pressure for a van der Waals gas is exactly this attractive term. And I thought that was super interesting that you can get that. And there is no way that you can derive this without using Maxwell relation. If any of you do that, you get 2 Maryland Dairy ice creams with me. If you can show to me that you can get the internal pressure of a van der Waals gas is AN square by V square, if you can derive this without Maxwell relation, I will be very, very impressed, and I will buy you, let's say, 3 ice creams. I'm so confident that you can't do that. And the reason being that let's stop at 2 ice creams, not 3. Let's do. There might be a way, actually, I just realized, but it's a good exercise to try. Maybe I'll be totally bankrupted. For the first person who does it, 2 ice creams. Okay, great. Okay, so this was our end of Maxwell relations. We go to next class. We again recapitulated our spontaneous change direction. And you can see why I have emphasized it so many times. Now you will be like, wow, you said the same thing every time, but you will forget it. You will forget it. Graduate students forget this, that this change for spontaneous, the condition for spontaneous change has a positive sign for total entropy of the system and universe surrounding. And for Gibbs energy at constant temperature and pressure, Helmholtz energy, constant temperature and volume, it has to be negative. Okay, so this was another application of Maxwell's relation. We calculated the entropy for a van der Waals gas, and we showed that it is proportional to log of V minus NB, which is a kind of a nice application. Then we started talking about phase diagrams, and phase diagrams are at constant temperature and pressure. Mostly they can also be temperature composition phase diagrams. We focused at the moment at constant temperature pressure properties. And in order to do this, we looked at G of T comma P. And we said that as per this integrated first and second law of thermodynamics, dG is equal to VdP minus SdT. Will you have time to go over fugacity? I won't probably, let's see, let's keep going. Let's see how far we get. I might post some extra material if you remind me on Slack, Jordan. I will post some extra material if I don't go over it. But I want to go over this thing because it's so important, and it shows you that partial G by partial T at constant T is equal to volume, and partial G by partial G by partial T at constant pressure is minus S. This relation showed up many, many times. Remember later when we did phase diagrams and we talked about complicated things such as these type of things, liquid plus vapor, liquid 1 plus liquid 2. This is the relation that showed up again and again. Here we realize that first of all, entropy is always positive. So that means partial G by partial T at constant pressure is equal to negative. So free energy always decreases when the temperature increases. So as the temperature increases, the free energy is going down. At zero temperature, gas is going to have the highest free energy, and liquid will be second, solid will be third. We went over this argument. It's summarized here on the right side by looking at the potential energy. But on top of that, we know that entropy for gas is more than entropy for liquid, is more than entropy for solid. It means that the three curves will be behaving in this manner. The entropy of gas will fall sharpest, followed by entropy of liquid, followed by entropy of solid. So the entropy of solid is kind of the flattest. The entropy of gas is the steepest. It means that they will cross each other at some point. And this is how you see that there must be phase transitions. Until a certain very low temperature, you can see solid is going to be the lowest free energy. Does the U graph only include PE? Which U graph? The U graph is potential energy plus kinetic energy. This one is potential energy. This one is talking about potential energy. That's correct. The reason we don't talk about kinetic energy here is because we are talking about zero temperature, right? So zero temperature, you don't care about kinetic energy. Everything is stopped. Nothing is moving. That's why at 0 Kelvin, we don't need to care about kinetic energy. And we were talking about the behavior at zero temperature, right? That's the idea. These things are subtle. It's easy to get confused. So we use these three arguments again. At zero temperature, G gas is more than G liquid, more than G solid, and that's why these things drop. So this simple thing, if you get it, all of the later phase diagrams are actually not complicated if you understand this. Okay, let's keep proceeding. We did 1023. Now we go to 1026. All right, fugacity is here. Your dreams come true. So we wrote down that dg is equal to v dp minus s dt. This is also a relation that shows up a lot. It's a bit harder to remember than the du is equal to tds minus pdv, right? Du is equal to tds minus pdv is easier to remember because that's just directly integrated first and second law. But these two statements are equivalent, and you should practice a few times in how to derive the left one from the right one and the right one from the left one. You can do both of them. Try to practice it. It's useful exercise. But one of the things we got out of here was that we derived many properties. We derived Gibbs-Helmholtz equation. There is nothing profound over there. I'm going to skip the Gibbs-Helmholtz. I want to get straight to fugacity. One of the things we showed is that, and you see I made a side sign because fugacity is complicated, however it matters. Partial G by partial T. So partial G by partial P at constant temperature is equal to volume, right? So partial G by partial P at constant temperature is equal to volume. Therefore, if you are varying the pressure from Pi to Pf at a constant temperature, you can integrate this equation and write down as Gpf is equal to Gpi plus integral Vdp, right? Now, if you assume perfect gas, this is no assumption. This is no assumption so far. But if you assume perfect gas, then you can write down V is equal to RT by P for 1 mole, okay? And you can now integrate this. You get Gpf is equal to Gpi plus RT ln Pf by Pi. This equation is true only for a perfect gas. You can set in the reference pressure. You can take the reference pressure as 1 bar. If you take it as 1 bar or 1 unit, whatever unit you're measuring your pressure in this, then sometimes this equation will just look at G is equal to G is equal to G naught plus RT ln P. When you say RT ln P, all you have done is to set the reference pressure is equal to 1 unit in the whatever unit you are measuring. You can make this plot. You can see that G goes to minus infinity as the pressure goes to 0. We have had nice discussions about this on Slack as to why does this make sense for an ideal gas. This was quite nice. It later came on homework also. So This relation, however, G is equal to G naught plus RT ln P by P naught, is true only for a perfect gas. People loved it so much that they said that, well, what about a real gas? Clearly, this is not going to be equal to true. But for a real gas, if I set some reference pressure and plot, so let's say I set some reference pressure P naught, at which I set my G equal to G naught, okay? And then I plot G minus G naught by RT, okay? So if I plot G minus G naught by RT, for an ideal gas, it should look like ln P by P naught, right? For a real gas, it will not look like ln P by P naught. It will look as ln something else. What is that something else? We don't know. It will be something else. And that something else is called F by P naught. You measure your G minus G naught divided by RT. So the definition of fugacity can be written as F by P naught is equal to e to the power G minus G naught by RT. That's our definition of fugacity. It's really mind twisting. It comes from, it's like doing this. The advantage of doing this now is that you can indeed write down your G is equal to G naught plus RT ln F by P naught. Would you want us to be able to write fugacity for van der Waals gas? It looks like you're giving me ideas for more problems for exam. I don't think you can do that. I don't think you can calculate fugacity just for van der Waals gas. It's tricky. You can think about it. I won't ask you on an exam. That's okay. This is a good practice problem, Elizabeth. Can you try to solve it? You'll get some good practice out of this. Or anyone else in the class who wants more problems. Can you calculate fugacity for a van der Waals gas? I don't know. Can you do it and tell me whether it can be done or not? I'm not so sure. I have to think more. But one thing we did here is to say that this fugacity is, we defined yet another thing called fugacity coefficient. We say that the ratio of fugacity by pressure is the fugacity coefficient. So if phi is equal to 1, we have an ideal gas. Fugacity is indeed the pressure. If phi is less than 1, if F is less than P, then we have attractive forces dominating. If phi is more than 1, then we have repulsive forces dominating. And so the point being that G versus F will always look like this nice behavior. G versus P will not look like that nice behavior. It could look very complicated. Here I'm showing you ideal behavior in black, and you have a blue curve which is below the ideal behavior for low pressures and above the ideal behavior for high pressure. So it shows you that the fugacity is more than pressure above a certain pressure. So if you don't have a lot of pressure, attractive forces are dominating in the system, and the fugacity is lower than the actual pressure, which is kind of makes sense, right? You have a room with not too many people, everyone is being nice to each other. Oh, no problem. Yeah, let's hang out, let's have a conversation. And suddenly you stomp in too many people in the room, you increase the pressure, and everyone is like, go away, too many people over here, right? So you can see why this plot makes sense. Below a certain pressure, you expect the fugacity to be lower than repulsive, than ideal pressure, and above a certain pressure, you expect it to be higher. So typically, many materials have sort of a crossover pressure at which this happens. Can you calculate this for a van der Waals gas? It's a very good problem. I'm definitely not going to ask you that on the exam, but I would like you to think about it. It's an open, you can think of it as a research problem. Can it be done? I don't know. And next class, we started talking about chemical potential. We said all we have done so far is dG is equal to VdP minus SdT, but what if it's a variable composition system? I'm not going to spend too much time on chemical potential because I have one full lecture 2 weeks ago where all I did was to talk about chemical potential in detail. And the lecture is on Slack. It's on the YouTube channel. It's also on, you don't want to see my diary. Where am I? What did I do? I was in 1028. Okay, cool. So we spent a lot of time talking about chemical potential. Mu In that lecture, we went over it in a lot of detail. Many of you wrote back to me separately saying that you found it very useful. So if you haven't gone through it, go through the video and also different notes accounting for chemical potential. Chemical potential is defined as mu I is equal to partial G by partial Ni at Tp, constant temperature, pressure, and every other thing held constant. You can also, this means that dG is equal to VdP minus SdT plus this. You could also derive chemical potential from other things. You could derive it from enthalpy, but now the things that are being held constant change. They become entropy, pressure, and Nj not equal to I. You could derive it for A, then you have T volume, Nj not equal to I. So doing, again, it's good practice to show that these forms of chemical potential are actually equivalent. There is nothing new in them. They are all the same definition. Then we talked about Gibbs-Duhem equation, where we introduced the notion of partial molar volume. And the thing to keep in mind here is that GI bar, and again, we spent two lectures at least going over this, revising this. I won't do too much, but that GI bar is equal to mu I. AI bar is not equal to mu I, and you can see why, because the partial molar of any quantity is always defined at constant temperature and pressure, while the chemical potential is defined at constant temperature and pressure only using Gibbs energy. If you're looking at chemical potential using enthalpy, you don't have constant temperature and pressure, you have constant entropy and pressure. For Helmholtz energy, you have constant temperature and volume. So it's the partial molar Gibbs energy is the same as chemical potential. Partial molar volume is not the same as chemical potential. Partial molar enthalpy is not the same as chemical potential. Okay, and we derived Gibbs-Duhem equation, which is typically written as Ni d mu I is equal to 0, but a more general form is Ni d mu I is equal to VdP minus SdT. So after that, I reminded you of direction of spontaneous change. And this is the material where, oh, this I had to do again because I forgot to record that video. So I went over this part again, the Gibbs-Duhem equation. And then this is all the same. We did not really do a new material here. We just derived the whole thing again. So that's good. Let's go to we are now in November. Okay, the one thing I do want to talk about today, as we are almost done, is something that you might have forgotten. We have spent a lot of time on phase diagrams. I'm not going to talk about phase diagrams. The thing I want to talk about is Clapeyron equation and Clausius-Clapeyron equation. Anyone remembers which class did we do it in? So I can directly go to that if you have it top of your head.
November 6th is where I see Clapeyron.
Great, thank you very much. Let's go to November 6th. Perfect. So yeah, we talked about phase boundaries, and the point we mentioned is that a phase transition is the temperature at which dG cannot be positive, dG cannot be negative, because two things are in equilibrium. So dG must be equal to 0. So, and if you are talking about a constant pressure temperature condition, so I'm skipping the Gibbs phase rule, and because we spent time over it, and again, I don't want you to worry too much about the derivation of Gibbs phase rule. I would like you to remember the formula for the Gibbs phase rule, F is equal to C minus P plus 2. So, but I want to talk about Clapeyron equation and Clausius-Clapeyron equation because it allows us to characterize phase transition. It allows us to characterize phase boundaries. The question we ask now is, given a pressure temperature phase diagram like the one we saw for water, what is the equation of this curve? So in order to do this, we said that two phases being in equilibrium means the chemical potential must be equal for both of those phases. And we are talking about one component system, so there is only one chemical potential. So mu at point A must be equal in phase alpha and phase beta. Mu at point B also must be equal in phase alpha and phase beta. We talked about differential change in mu, and from this we got a relation called Clapeyron equation, that dP by dt is equal to delta S transition by delta V transition. Clapeyron equation is very, very general. It does not assume ideal gas, anything. It's super general. And using this Clapeyron equation, we were able to show why the boundaries behave in a certain way, why some of them are upward sloping, why some of them are negative slope, downward sloping, what happens for water. Next time, we also look at an approximation to this equation, which is called Clausius-Clapeyron equation. For Clausius-Clapeyron equation, we assumed an ideal gas. And so this was our Clapeyron equation, dP by dt is equal to delta S transition by delta V transition. This is assumption free. There is no assumption over here. We then talked about a specific boundary, which is the where did we do it? Did we do it in this one? Yeah, we looked at all our different boundaries, and specifically, yeah, there it is. We looked at the liquid vapor boundary where we assumed ideal gas, and the other thing we assumed that V vapor is much more than V liquid. Once we assume these two, we can derive a separate equation which is called Clausius-Clapeyron equation. Even though it has two things in its name, it's less general, which says d ln p by dt is equal to delta vaporization h by RT square. So one thing you should remember is that Clapeyron equation is very, very general. Clausius-Clapeyron equation applies only to one boundary and only to ideal gas. So, and after this, we spent a lot of time talking about regular solutions. I just want to mention one thing about regular solution is that delta mixing is delta S after minus delta S before. How much did the entropy change? And we showed that for a two-component system, this looks like N. We can remove the N, we can talk about per mole. This looks like R x1 ln x1 plus x2 ln x2. And we spent a lot of time thinking about the properties of this function. This showed us that mixing, so this was our delta mix ideal. What is the mixing, entropy mixing for an ideal, if everything is behaving ideally? For ideal mixtures, we can also say that the gain in enthalpy due to mixing is 0. There is no advantage in enthalpy because there is no enthalpy. Ideal things don't really have any enthalpy. There is no internal energy. They don't talk to each other. So we talked about how this looks like. We drew our, there is immediately an entropy gain. If you talk about delta S, it looks something like this. As soon as you add anything, there is immediately entropy gain if it's an ideal behavior. Then we went to regular solution model where we introduced that, okay, well, for a regular one, maybe this is proportional to the mole fraction of the two species. So if we think about minus T delta S, that's going to be negative compared to this curve. But this term over here, omega XA XB, is going to look like this, while minus T delta S is going to look like this. And it's all about the competition between these two. And the richness of phase diagrams and miscibility gaps and final decompositions all happened from one very simple mathematical observation, which is that close to 0, minus T delta S drops down with a slope of minus infinity. So it always dominates. You are always going to be negative. But in between, you can either be negative or you can have funky behavior of all sorts going on. And that's really the origin of phase diagrams. If it was two-component system, the chemical potential of each component not equal with each other, just with the other phase of the, if it's a two-component system, then it's a good idea to look at the derivation of the Gibbs phase rule. That's where we talked about a general n-component system, right? So if you're confused about how to write down equilibrium for multi-component system, look at the derivation of the general Gibbs fees rule, and that will clean up everything. Okay, so please post more questions on Slack. I will try to respond as much as I can by Thursday night. Your classmates also, I request you to help. If you are confident on something, please reply. We will not be meeting. This is the very last class. I would have liked to meet you all in person, maybe got you cookies or donuts or something like that, or probably brought Pakara to class today, where you got to see him. And I hope you all learned something in this semester. Thermodynamics is not easy. PChem is not easy. Anyone who says PChem is easy is outright lying. You can quote me. It's not easy. It's hard. It takes time. You have to work through it. The exam is designed in such a way that all problems can be done in less than 3 hours. You have all the internet open for you. You can cheat. You can discuss with your friends. You are not doing the right thing if you do that. You are only defeating the purpose. There is something about type 2 fun. If you work through it and you get it, you are the one who will feel happier. And I'm going to be lenient in giving you grades. So why cheat? Don't try to cheat. Try to do it on your own. See how far you can get. Okay. And all problems, none of the problem is hard. They might require a bit of thinking, but you will get it. And again, if you have not submitted the course evaluations, please do that. I will be very, very grateful. It will help me improve as a teacher. And this Slack channel will be open always. I'm never going to shut it down. It's for you all the time. It will always be there. When you become the CEO of some company or something and you have $1 billion investment requiring a phase diagram, you can come and discuss with us what to do. So, and yeah, so the Slack discussions will happen till Thursday night, Friday morning to be technical. I won't be responding Friday early morning, but that's when we will stop Slack and the exam will be out. The PDF will be released on the class website. It will also be on Gradescope. You will have to submit through Gradescope. Okay, take care everyone.
Thank you.